Okay, so I guess I can start. It's already like 10. So thank you everyone for being here. So today I will mainly talk about the spin texture of chain bands in this AB-stacked transition metal dichalcogenide bilayer. And first I will give you like a kind of overview of what we have already achieved and what we can expect in this bilayer Moiré system. So the talk is mainly based on two recent work. One is theoretical on the kind of topological features of this AB-stacked bilayer, and one is the experimental work on the quantum on the experimental quantum mass Hall and quantum spin Hall effect in the MoTe2 and WSe2 bilayer. So first, let me thank my collaborators. So it involves like my supervisor Liang in MIT and Chris Devakul, postdoc in his group, and also Jason and King-Fan Mac group in Cornell. And I also acknowledge the collaboration with Hiroki Isobe, who is now in Tokyo, and Noah Yuan in Shenzhen, and Tongtong Liu, and also Tim Xin and Shen Wei for their collaborations in the experimental side. Okay, so maybe let's have a brief introduction of this Moiré structure. So a Moiré structure can be achieved from a kind of a uniform material in two ways. In a homobilayer, there is no lattice match. And when you introduce a small angle to van der Waals material, would have like an interference pattern. And then you see a long range kind of a lattice, which is like a nanometer range, like 10 or 100 times larger than the original kind of unit cell. And another way to achieve the Moiré lattice is in a heterobilayer, where you already have this kind of lattice mismatch. Because there's a lattice mismatch, so in a long wavelength, we also can see some like Moiré patterns for different stacking regions. And then this form a kind of effective Moiré lattice. Okay, so as we all know, that this Moiré physics kind of attract our attention because of the fused bilayer graphene, and which we can call it kind of semi-metal Moiré. And what I'm going to focus on is main in the TMD Moiré is so-called a semiconductor Moiré. So what's the key difference of these two kind of Moiré system? So in the fused bilayer graphene, so the Moiré bands is formed from the massless direct fermion in a periodic potential because we have zero mass in this direct fermion bands. And then, so everything only happens at a small kind of parameter region called a magic angle. So everything at this magic angle, and they are also very disorder sensitive to many kind of lattice disorder or even the magic angle disorder. And so the kind of the charge and spin distribution of freedoms they are really complex. However, in this semiconductor Moiré, the Moiré bands are formed from the parabolic bands at the band top, separated by a large band gap. So in the end, so we have like a kind of a simple scenario, like the electron moving in a periodic potential. So and then we can control various kind of the bandwidth and the interaction U by varying the tooth angle. So right now we have a much broader parameter region for the interesting physics to happen. So in this semiconductor Moiré, mainly we have like three types of this complexity. So in the beginning, people have investigated this heterobilayer WSe2 of WS and WS2. So in this case, and we have the holes in the WSe2 layer moving in a periodic Moiré potential generated by the WS2 layer. And so in this system, the charge carriers are moving within one layer, so the tunability is relatively low. So very strong correlated physics has been observed here in analogs like the Wigner crystal and many fractional filling insulin state. And a second kind of level Moiré can be found in this two-state MoS2. So right now, still we have this. We can roughly describe the system as the charge carriers moving in a periodic Moiré potential. But the thing is that because the charges are kind of trapped in bonding and anti-bonding orbitals of two layers, so the Moiré potential can be controlled by varying the gating field. So in this system, we achieved kind of electron in a periodic tunable potential. So, and then in the third level system, for example, this Tuesday WSe2 and WSe2, and also in the focus system MoTe2 and WSe2. So because here we have a like kind of complex tunneling, and this complex tunneling further entangles two layers, and then we achieve the kind of we have a kind of imaginary wave function, which gives a possibility for topology. So first two level system, they do not have topology, so they are kind of roughly, they can always be understood in the tether-bonding limit. Right now, in the third level system, because this complex tunneling term, we may expect there might be some like topology, emerged over previous correlated state. Okay, so to begin with, maybe I can have a a brief introduction for this transition metal dichalcogenide, this MX2. So these 6 materials coming from the combination of tungsten, Moiré, and terra-cyanide sapphire are the most well-known semiconductors. And the feature, the band structure, their band structure featured a large gap with the parabolic bands at the K point in the monolayer form. And there's a large spin valley locking because of the MZ symmetry in the plus K and minus K valley. And because of the spin valley locking, so the spin is almost fully polarized at least 2 layers, at least 2 valley, K and K prime. Okay, so this is the feature of the single particle bands. And then when they form a Moiré band, we can roughly understand this from, for example, this is a Moiré radical of WSe2 and WS2. We can roughly understand the Moiré band structure as a kind of special modulation of the valence band top at K. So the valence band top at this K point, at this big K, they would modulate, they would have a modulation because of the Moiré potential. And this can be modeled by a very simple Schrodinger equation with this kinetic term and the potential term to model the spatial modulation. And in the simplest kind of approximation, we can expand the Moiré potential in terms of 3 Fourier harmonics because the original system has at least 3 kind of rotation symmetry. And when we expand the Moiré potential, so in these 3 harmonics, and then in the end, we find that the parameter involved in this continuum model is very simple. We only have this effective mass and the potential strength and this phase factor phi. So these are 3 important parameters determine the properties of this system. Okay, so and then maybe we can also talk about the Tuesday angle. So this is a plot of the Tuesday bilayer MoS2. Also can be understood in the tether-bonding limit. So as we can see, when we vary the Tuesday angle from 6 degrees to almost 1 degree, the bandwidth goes from like 250 milliV to almost 0 milliV. So we have a kind of continuous tuning from the dispersive band, which is nearly free electron-like, to a really narrow band that goes to the tether-bonding limit. So in this system, we can really realize a highly tunable bandwidth and the interaction strength. Okay, again, yeah, as we mentioned before, there are 3 key parameters to describe the single particle Moiré bands. So for the kinetic energy and for the V, maybe we have a very good feeling of that. And then this Moiré phase factor phi is also very important. So this determines the effective kind of model. So if we choose this phi from 0 to 1/6 pi, and then the second Moiré band would be coming from the p orbital of the region. And then if we choose the phi in this region, 1/6 and 1/3, then they will come from the s orbital of the xm for this parameter region. And then we can call the top band as a Moiré cation and xm as a Moiré anion. So right now, the low energy effective theory can be captured by this effective honeycomb lattice with two different Moiré sites acting as an effective atom. So this can be kind of has a chemistry analog like the super atom. And we have like an artificial kind of super solid because of the landscape of this Moiré potential. Okay, and then by tuning this kind of V and U, we can achieve different phase diagram in this simplest system modeled by 3 parameters. By changing the U, we can tune them from a metal to a Mott insulator. And this is the case that this charge transfer gap is smaller than the U. When we further increase the U, as we can see, when U is larger than the potential difference of this MM and MX region, so at n equal 1 at half filling, when we further drop charge inside, the charge would fall to another Moiré region, not to the up Hubble band. And this is the so-called charge transfer insulator. So only by 3 kind of parameter, we can already achieve a metal Mott and a charge transfer insulator. Okay, so in this simplest system, so what have been achieved? So people have observed this correlated Moiré states in a bilayer transition metal dichalcogenide, typically in this WSe2 and WS2 system. As I have mentioned before, in this effective Moiré lattice, there is a variety of insulating states that are observed at a series of fractional fillings. And also there are a kind of signature of the kind of magnetism, which so in this system. Okay, so let's go to the charge order of this WSe2 and WS2. As we have mentioned, so because the one-year function are strongly localized at one region, then we can view them as a kind of artificial solid. So as various conventional filling, so they would spontaneously forming some like generalized Wigner crystal, as we can as experimentally have seen. So many kind of fractional fillings. Okay, and also this important like 1/2 filling, we can achieve different symmetry breaking state that typically break the C3 rotation symmetry to minimize the interaction Coulomb energy. So there are different type of these stripe orders that have been observed by this optical birefringence. Okay, so then I would talk about another kind of system, as I mentioned, the homobilayer MoS2. So this has not been intensively experimental or investigated. So in previous system, there's a large charge transfer gap, and everything is kind of the effective lattice is kind of fixed. In this homobilayer MoS2, so with 0 different field, as you can see, so the single particle, this is a band structure from large scale DFT calculation. You can see Devakul emerged because of the C2Y symmetry in the Moiré lattice that connects the XM region and the MX region. And if we break this C2Y symmetry, it's possible to introduce a kind of charge gap at this Dirac point. And what we really do is that we introduce a charge transfer gap between these two Moiré regions. And so in this system, so we can achieve a kind of a tunable honeycomb lattice. the effective model for this system is relatively kind of, we have another degrees of freedom, which is the layer degree of freedom. And then, so that one is modeled by this interlayer tunneling term. So as I mentioned before, so the effective continuum model for the WSe2 and the WS2 is the kinetic term plus a potential term, 3 parameter. So in this Tuesday MoTe2 system, we have this interlayer tunneling term, which is modeled also by a few cosines. So this interlayer tunneling terms give rise to the anti-bonding and anti-bonding orbitals, and so the interlayer tunneling for this gamma valley is pretty large at like 200 millieV level, and they are solely depends on the interlayer distance. Okay, so when we tune the potential of this MoTe2 MoS2 layer by some gating field in the single particle level, if we plot the gating field dependence kind of parameter, the bandwidth, the also the charge transfer gap data, as you can see, so the gating field kind of linearly increase the charge transfer gap. So in the effective extended Hubbard model, so what we have is that, so right now, so besides this interaction, the local interaction U and the extended interaction V, we have further the tunable charge transfer gap data. And when tuning this data, we can achieve a series of charge orders going from the side balance state to side fully polarized state. So different colors meaning two different Moiré sites. So by kind of changing the charge transfer gap between two Moiré regions, we can change the low energy ground state of this charge order. Okay, so actually the most interesting and the kind of highest energy scale in this insulating charge order is what we call a Mott ferroelectricity at n equal 1. So as I have mentioned, when we tune the charge transfer gap data, we can achieve different set balance state and set fully polarized state because those two sites has different kind of layer weight. So a side fully polarized state will correspond to some like layer polarization. So particularly at n equal 1, to minimize the nearest label interaction repulsion, and the charge order ground state would be a side fully polarized state. So even when data is equal to 0, we can achieve a kind of side fully polarized state that give you a z direction ferroelectricity. So, and then, so this is a new type of kind of ferroelectricity that is generated by the kind of Mott physics. And when we estimate the polarization of this system, actually this is even much larger than the typical lattice ferroelectricity. Okay, and also the energy scale is relatively higher because the Lex label interaction V is as large as like 10 millieV. So this Mott ferroelectricity label happen even at like 100 Kelvin. Okay, so we have introduced like, so by now I have introduced like two specific Moiré systems that's very pretty simple, which can be modeled like by two effective Moiré solutions of two Moiré regions. And above that, so as we can see, so this kind of semiconductor Moiré system, so they can be really viewed as these artificial solids made of emergent superatoms. And the effective model, so no matter whether the kind of interlayer tunneling, so can be always captured at the simplest level by this simple Hamiltonian if we add the interaction term. So this is the kinetic term. So this is the potential term, and this is the kind of Coulomb energy. So in a simple solid, the V is kind of ironic potential, but right now in our artificial solid from this semiconductor Moiré. So the potential is from the slow varying Moiré potential, which spans at like 10 nanometer level. So in this artificial solids, so actually, so we can always find some like energy scale. So especially so at this TMD, because of a large effective mass, so the RS is very large already, at least relatively achievable of the carrier density. So like so we can already achieve like a very strong correlated physics in this TMD Moiré. So okay. So based on this effective Hamiltonian and also the simple understanding, so maybe we can design a different kind of computing kind of principle for the Moiré system, as I will describe later as this Moiré density functional theory. So I showed a lot of band structure of this Moiré system. So one hidden kind of difficulty in this system is that the computational cost for the Moiré bands is really insane. So when we, in the first case of the reduced bilayer graphene, when you have like 10,000 metons, so at the first time when they want to relax the lattice structure and also calculate band structure, they use like over like 1 million cores in a K computer, the biggest supercomputer in Japan, because the density function theory calculation for such a large system is really huge. So in the Q3 MoS2 system, which I carried this calculation, so the computational cost is like nearly like 4,000 cores with 16 terabyte memory for 3 days. So this kind of unbounded kind of computational cost because of a large Moiré length really limited our prediction power of this Moiré system. So as I mentioned, in your DFT, we really direct target the ionic potential. So right now, but in the Moiré system, we can really forget about the original solids. So original solids is so complex that kind of there are special divergent ionic potential. So if we replace this 3D singular divergent Coulomb potential to a smooth varying Moiré potential. So as we know, this V0 maybe is only like 20 or like 20 millidj level. And by these two parameters, we have like a effective pseudo potential of this Moiré system instead of previous complex potential. So right now, our target is this very free Moiré electron, maybe less than 5, instead of previous like 10 to 6 electrons. So why do we really need to kill the core electrons in the original solids? So what we really need to kill is the very free Moiré electrons in a low energy Moiré potential that really give rise to the interesting physics. So for this effective Moiré potential, we can now apply its constraint density function theory to the above, to this Hamiltonian. So basically, we solve this Hamiltonian by the Coulomb potential and also the exchange correlation function. So as we know, so a simplest kind of density function is the so-called local spin density function approximation. So which is generated from the homogeneous electron gas. So this LSDA is exact for the homogeneous electron gas. And again, in our Moiré system, because of the free, because of the kind of smooth Moiré potential, this is much like the case as the homogeneous electron gas. The density is only slowing and also smooth varying in terms of the real space. So this is the actually exact kind of ideal situation for the LSDA function. Okay, so using this Moiré density function theory, so we basically calculate the filling-dependent magnetic properties for various material orders. For example, in the previous bilayer system WSe2 and WS2. And we look remarkably, so we find that near filling 1.3, this is much like, so the low energy state actually is a ferromagnetic state, which is really distinct from the simple understanding of the undifferentiated order from Hubbard doped Hubbard model. So, and then when we actually this kind of ferromagnetism at n equal 1.3 reminds us the ferromagnetism in two-dimensional electron gas, as we have known. So at low density limit, at least large RS, the kind of the spin polarized fluid is the lowest energy ground state. So do we have something similar here? So we perform a calculation actually in terms of the total energy with the potential from zero potential, which is a free electron gas, to like 18 millieV. So that's the, so this is the Moiré potential in the WSe2 and the WSe2 system. So as we can see, the total energy of the fully polarized state they drop down much faster than the non-polarized state. So, and then the physics or the ferromagnetism here is really ideal, so kind of adiabatically connected to the ferromagnetism of the free electron gas. Okay, actually, so what I have mainly talked about until now is kind of the single layer physics, where we have a very simple modeling as a charge carrier moving in the effective Moiré potential. So how about this? How about this really the two-layer system? For example, the MoTe2 and WSe2. So where charge carrier, they are really in both layers. So recently, there is this unexpected experiment work. So they observe the quantum anomalous Hall effect from the AB-stacked MoS2 and WSe2. Actually, in the beginning, this is very surprising even to us. We have worked on this Moiré kind of physics for like more than 2 years. And this is really surprising because in the AB-stacked system, the spin, the Moiré bands in 2 layers actually they have opposite spin. So this means they would not really interact with each other. So, and then what's really the origin of this Moiré physics? So, okay, this is a little on the experimental data. So in this MoTe2 and WSe2 system, this is the kind of getting map of the 2D sample. As you can see, at least V equal 1 region and the filling V equal 1. So when you plot this RSX, and then you find some metallic state smoothly connected to this Mott insulating state. And then when they measure the RXY of this metallic region, they remarkably find this zero field quantum anomalous Hall. Even at like the auto temperature is around like 2.5 Kelvin. So this is actually much larger than the previous doped the doped topological insulator. So yeah, so when we first come to discuss with the experimental group, actually we are quite surprised. So why we have this kind of topology in this system rather than the AA system? So in the MoTe2 and AB-stacked MoTe2 and WSe2 system, so when we look at the effective band, when we look at the effective band structure, there is a large kind of layer split. There is a kind of layer potential difference, and then the two Moiré bands actually they carry different spins. When we move them together, can they really get inverted? Because naively, if they are fully polarized, we would expect a zero tunneling. So then they would not really invert and get this topological gap. Okay, so right now, if we look at the valence band offset of this MoTe2 and WSe2 layer, so there is like 100 millieV energy difference. So what the gating field really do is to push the black line is the WSe2 monolayer bands. So here we just overlap the single particle band structure of untilted one by one unit cell to see the feature of the building block. Okay, so when we move the WS2 bands further higher, and then they would intersect if it's the MoTe2 band. But as we know from this red picture, they are opposite in spin. So naively, we would expect zero tunneling effect. Okay, so actually, but then, so this simple understanding actually does not hold in terms of the Moiré superlattice. So as we know, when we stack the Moiré superlattice together, locally the environment are very different. We form this MX region when the metallic atom of the top layer is aligned with the Chern atom of the bottom layer, and then this MM region when the metallic atom of two layer they are aligned, and XX region when the Chern atom of the two layers are aligned. Because of the local environment, the geometric difference of a local environment, actually there's a large corrugation in the Moiré scale. So as you can see here, I plot also a 2x2 Moiré space. So when we plot the spatial dependent kind of layer distance, so as you can see in the XX region, because of the direct alignment of the Chern atom, the layer distance is 7.4 angstrom. But in MM region or in the MX region, because they are kind of offset, so the layer distance is only 6.8 angstrom. So in the end, so the monolayer are strongly correlated. So that means the MZ symmetry is broken here. So which is key to our following discussion of the breaking of this spin conservation. Okay, as we have seen from the Moiré band structure, again, so because there is a large band offset of the two layers, so in a zero diffusion field, we can roughly understand the Moiré band structure from two layers separately. So if we plot the Boolean zoom of the MoTe2 and the WSe2, this kind of schematic figure in the WSe2, so in 0 degree Tilst device, we have like 14 by 14 WSe2. So the minus K value is the minus K value of the original monolayer. So this green and the blue lines are the Boolean zone for the one by one unit cell, and this small Boolean zone are the milli Boolean zone because of the folding. So when the WSe2 band structure K minus K folds to the Moiré band structure, so they form the band structure at this kappa point of the Moiré Boolean zone. And then when the minus K value of this MoT folded to the Moiré Boolean zone, they go to the minus K value. So as you can see, so right now we only focus on the minus K value because the Moiré physics actually in the single particle model and also in the correlated model physics, those two values are strongly decoupled. So we can always looking into one value. So for this minus K value, as you can see, so the parabolic band at this minus K, so at this minus K value, they fold band to band top of the kappa prime, and then forming this Moiré band. And in WSe2, oppositely, this minus K value fall to the kappa point of the Moiré Boolean zone. So they fall to this kind of blue lines. More remarkably, as you can see from this WSe2, so this is much like the free electron gas limit, where Moiré potential is almost zero. So the Moiré potential controls kind of the splitting at this kappa point. When Moiré potential is zero, we have a free for degenerate at this kappa point here. So as we can see, so the band structure of the Moiré space, I mean in a monolayer, here the calculation is performed when we separate two layers and they do not interact, assume they do not interact with each other. So, and then when we look at the band structure of the Moiré superlattice, as we can see. So let's remark. So the previous Moiré band structure for multi-layer and MoTe2, there are 3 bands near at least kappa point. So, but right now, if we look at the heterobilayer band structure, so this is the plot for the heterobilayer band structure. Actually, we have 4 bands here. And then when we look into the wave function, the special localization of this 4 band structure, there is 1 band from the WSe2 layer, which is the band top of this WSe2 Moiré bands. So what this scattering field really do? So they just reduce the potential difference and moving the WSe2 band higher and higher. So gradually crossing at least critical field. This is the WSe2 band, and then later opens this band inversion. And if we plot the topology, if we plot the gap at kappa, actually we see a closing of and the reopening of this gap. So the message is that this displacement field inverted the MoTe2 and WSe2 KO minus KY bands at kappa and kappa prime. So, but they with nominally opposite spin. And so this band inversion leads to the valley Chern bands. And then right now in the computational level, actually we demonstrate there is a band inversion. But physically, why we have this band inversion between these nominally opposite spins? As I have mentioned, in the Moiré superlattice level, the MZ symmetry is kind of broken. So that gives us some hope. So because of the break of MZ symmetry, maybe the spin is not conserved anymore. So that spin U1 symmetry is broken. Okay, so right now when we look into the spin and the layer resolved wave function, actually that's actually what we really found. So remember, in the Moiré band structure, so typically after band inversion, we know that these top 2 set of Moiré bands are forming from the MoTe2 bands, and then this Moiré bands goes up is the WSe2 Moiré bands. When we look into them, so plot the layer and the spin resolve the wave function. So and then now we are just plotting the wave function of the 2 Moiré bands separating. And as you can see, so actually they are both. So the top band, the majority layer is this WSe2, which has this unit of 1.0 maybe. And then, but there is also a significant contribution from the MoTe2. This is maybe 10% in terms of the amplitude. So why is this mixing possible? Yeah, because in the in his Moiré bands, the spin is not conserved right now. At the majority layer, in the MLT2 layer, actually you can see that the spin up and the spin down component, they are roughly comparable to each other. We have both the spin up and spin down. So this spin up component of 2 layers opens the possibility for the finite tunneling omega. Okay, so right now, if we look at the bottom topological bands, that's also the case. So although the majority layer right now is the MoTe2, we have also a significant contribution from the WSe2 layer. And then the spin, so there is also a spin down kind of contribution for the bottom topological band. The bottom topological band, which opens the possibility for the non-zero tunneling time. Okay, so the message of this plot is that the spin U1 symmetry actually is inexact due to the broken MZ symmetry. Or there might be other. So in the first order, we can imagine this direct hybridization is responsible for the tunneling effect. But there might be also some like high order tunneling to the same spin band to the same spin bands, I mean between the two layers that differs large in energy. Okay. More remarkably, when we plot the spin texture of the minority layer, so this is the minority layer plot of the two topological bands. Actually, we can see the spins are forming a skirming-like crystal going from XX region to the MX region. So here I plot the z direction spin moment as the red and blue, and then the X and XY as a vector. So we can clearly see there are source and joins in the real space in both topological bands. So this is kind of a direct illustration. So kind of illustration of the origin of the topological Moiré bands. Okay, so right now we understand that there's a finite interlayer hybridization. This finite interlayer hybridization is quite small compared to other kind of homobilayer system. So in a homobilayer WSe2, because the tunneling is directly in the same spin bands, so the tunneling magnitude is roughly like 20 millieV. But here, as you can see from the layer plot, the spin kind of the opposite spin bands are roughly just maybe 10% of the same spin. So I mean in the first topological bands, as you can see, the layer weight of the MoTe2 is just like 10% of the WSe2. So here we also expect the interlayer tunneling should be like one order of magnitude smaller in the case compared to the case of the homobilayer WSe2. Okay, so and then to model this system, we also write this continuum model, as we have seen in the case of the MoS2. So beyond this single layer dispersion, the kinetic term plus the potential term, we have further this interlayer tunneling term. So here, the intertunneling term can be expanded over 3 harmonics, and these harmonics can be kind of further understand in terms of the minus k, the C3z eigenvalue of the minus k value, which form the Moiré band. So in the end, we have these complex tunneling terms as so in the off-diagonal terms. Using this continuum model, we fit the DFT band structure. So as you can see, so this is the DFT band structure after band inversion. This is the zoom in at the band inversion point. The continuum model captures the band dispersion at its couple point at the band inverted point really remarkably well. And in terms of the band gap, as you can see, if we calculate the minimum topological gap between these two layer bands, we can see a closing and reopen of bands at 2 milliev level, which is very consistent with the experiment. So this is the experimental charge gap at mu equal 2. Okay. So in terms of the continuum model, actually we still need to calculate maybe the Chern number of these two bands to determine whether it's topological or not. But there's a simple way that we can understand why we have this topological band at the Moiré system, which is the so-called symmetry eigenvalue, C3z symmetry eigenvalue. So when we diagonalize this two band at a couple point before inversion, so we can always calculate their symmetry eigenvalue from density function theory. From the original density function theory, we find that their symmetry eigenvalue is different. So because of the different symmetry eigenvalue, so they can get inverted and open a topological gap. At the continuum model level, so we can also understand this from two separated monolayer continuum model. So here, because the turn is very small, as I have mentioned, this is only like one order smaller than the home bilayer case, and it's only like 1.2 millieV. So this turn can be always viewed as a small perturbation. So the essential physics here is governed by the band dispersion of two separate layers. Starting from these two separate layers, we can calculate the symmetry eigenvalue as its kappa point from the symmetry eigenvalue of the k value, the minus k value of the unadjusted monolayer. When we calculate the two symmetry eigenvalue, and if they are different, this symmetry eigenvalue of the WSe2 band top and MoTe2 band bottom, they are different. So they would open a topological gap. But right now, in this system, because this in this system, if we go to the A stacking, actually we will find that the symmetry eigenvalue become the same. So this explains why A stacking band structure is non-topological, and we do not see a autonomous hole in the A stacked case. Okay, so finally, let's go to some like kind of analog of these topological bands. So the message for the mechanism here is we achieve this topological band in this bilayer system. So as long as the symmetry eigenvalue of these two layer bands they are different, they can get inverted open a topological gap. And these topological bands can be captured by, the low energy model of this low energy continuum model. This is a massive Dirac Fermi model. And they can model the same rules of this Dirac mass can model the change of the Wally number from 0 to 1. So in this period, when the interlayer hybridization is a weak perturbation, 1 or 2 millieV, much smaller than the kinetic or than the kinetic energy scale, we can always expect such a topological bands. So that means we have many more possibilities in this bilayer semiconductors. So in bilayer semiconductors, so I didn't say Moiré here. In Moiré, for sure, we will always expect these bilayer topological bands. And because the correlation can be always tuned by the tooth angle, and then we can achieve this topology together with the correlation of the bilayer semiconductor Moiré. So in the end, I would also refer to previous work, a very profound work of Chern Liu. And so where they design these topological bands is bilayer quantum well in indium arsenide and gallium antimony. So as you can see here, the two bands from two quantum wells, they also have different symmetry eigenvalues, band characters. When they are tuned to the same energy by the gating field, they also open a topological gap. So even in the untwisted semiconductor quantum wells, we can already see these topological bands. So the topological bands in the semiconductor Moiré further introduce a correlation into these topological bands. So the strong correlation or the local regression you hear makes the highly polarized state possible, which transform this topological insulating state at n equal 2 to n equal 1 quantum anomalous state that is experimentally observed. Okay, so this goes to the end. So in the first part, actually, I explained that semiconductor Moiré lattice with this 100 or 10,000 atoms can be mapped to an artificial crystal, unlike the complex semi-metal Moiré. So The effective artificial crystal, they can form a metal satisfying insulator and a molten insulator. The correlated ground state, especially charge order, can be tuned if we can tune the Moiré potential, as in the case of two-state MoTe2. In the second part, I have shown that the topological bands and can also be found from this inverted bilayer semiconductor moires. When we view the interlayer tunneling as a kind of small perturbation, so we can always think of like two separate layers get a small banding inversion. This provides a highly tunable platform called a quantum spin Hall directly. So we expect this equal to quantum spin Hall because of a very contrast Chern number. And then when we introduce an interaction of, so when the variance is further enlarged, so the very fully polarized state will directly give us a quantum anomalous Hall effect. So the inverted bilayer Moiré systems provides a further topological platforms, which is really robust and highly repeatable. And I would expect many more such systems will be discovered in the future. Okay, so that goes to the end of my talk. So feel free to ask any question if you have. Okay. Yeah, please, Anton.
Yeah, thanks a lot for the talk. So I'm not an expert on the Moiré heterostructures of the non-graphene materials, but if I remember correctly, just the regular behavior of these materials, the material quality is much worse there. So so there's more disorder, etc. Can you comment on the role of just the boring disorder in creation of these heterostructures?
Yeah, this is a very good question. So disorder has like two different kind of influence. So for example, so that can affect. So for example, the magic angle disorder in this Semimetal moire, they affect the bandwidth or the bandbag gap there. So because the bandwidth of the Semimetal moire are very small, so they are extremely sensitive to a local disorder or this kind of angle disorder. But as you can see in the Moiré system, especially in the MoTe2 and the WSe2, so the bandwidth is almost like 16 millieV, the single particle bandwidth. So they are very robust in terms of a local kind of alignment disorder from the kind of maybe an angle, maybe a roughly like 1% or maybe 0.2% change of the angle. So they would stay still very robust. So in TMD Moiré, the physics, as I can say, is kind of continuous. So we would expect the same thing at a range of this angle, unlike the Semimetal moire. So yeah,
but this only partially addresses my concern, because so I agree with you that the alignment disorder is a lot less important, especially since you are focusing on the gamma point physics. But at the same time, the underlying material is, so graphene is impressively clean by now, and like MoTe2, tungsten ditelluride, all of these materials are their mobilities are orders of magnitude lower, right? So it's the underlying disorder and not the alignment disorder that worries me instead.
Yeah. So yeah, that's the second type of disorder. Yeah, I would mention. So for this second type of disorder, so as you know, in the WSe2, so right now carrier density can go to like 2 times 10 to 12. So that's the kind of present limit, so which you can probe. In terms of the MoTe2, so in terms of MoTe2, so right now they can also go to like 2 times 10 to 12 in this experiment. So in this Cornell experiment, they can probe as low as like also 2 times 10 to 12 carrier density. So more remarkably, in the MoS2 system, right now in MO system, they make really clean MoTe2 sample, and they can go to the 10 to 11 even in the optical measurement. So the situation is getting better and better in the TMD Moiré. So maybe we can access to the even larger Moiré wavelengths. So as you can see, so right now, actually all the correlated material physics in the TMD are observed like maybe 5 nanometer or to 8 nanometer. So, but in the future, maybe we can go to maybe 12 or even to 20 for even stronger correlated physics.
All right, thanks.
Thank you. Okay, yeah. If no further questions, maybe yeah.
Well, okay. Actually, since there are no further questions, I could perhaps ask another one. So another thing I'm wondering about is gating. So, do you know if people successfully gate these devices, and like if local gating is successful?
Yes. So as you can see here, so in the MoTe2 and WSe2 system, so the autonomous hole is only possible when you gate the sample. So because originally there's a 100 millieV, around like 120 millieV band offset of the 2-layer. So the physics only happens when you further increase the kind of valence band of this WSe2, and then they get inverted and they form this autonomous hole state.
So, but that's a global gate, right? That's not a local one.
Yeah, local gate, that one I'm not sure actually. So.
All right. Thanks a lot.
Yeah, thank you. Yeah. So that's all. Yeah. Yeah. Thank you for everyone for coming. Yeah. Bye.